For basically all of human history, we've relied on fire for power. But what if the way we think about fire is actually what's holding us back? What if we could make it cleaner, way faster, and just more powerful than we ever thought possible? Well, that's exactly the idea behind something called plasma-assisted combustion. And look, this isn't just some sci-fi fantasy. It's a real question that's driving a whole new field of science. The mission? To unlock the next generation of energy, of propulsion. Basically, to take combustion, the thing that runs our entire world, and perfect it. So here's how we're going to break it down. We'll kick things off with the race for cleaner engines. Then we'll get to the secret ingredient that's changing everything, plasma. We're going to dive into what makes it so special, its 3 superpowers, really, and then look at some absolutely mind-blowing test results. And finally, we'll look at what this means for, well, the future of fire. All right, let's get into it. First things first, why is this even such a big deal? Why do we need to perfect combustion right now? Well, it all boils down to one huge global challenge. Just try to wrap your head around this number. Over 80%. That's how much of the world's energy comes from, well, burning stuff. And yeah, it powers our lives, but it's also a huge source of greenhouse gas emissions. If we're serious about our climate goals, we don't just need an improvement, we need a massive fundamental breakthrough. So what's the big hope on the horizon? For a lot of folks, the answer is hydrogen. I mean, it's an incredible fuel, right? It's packed with energy, and when it burns, you get water. That's it, 0 carbon. But, and this is a big but, hydrogen is really tricky. It's tough to ignite reliably and even harder to control, especially when you're talking about the insane conditions inside a modern engine. It's like a hero with an Achilles heel. So how do you fix hydrogen's big problem? Well, scientists are turning to this amazing secret ingredient. It's the 4th state of matter, something you've seen in the sun or in a lightning strike, plasma. But here's the twist. It's not the kind of plasma you're thinking of. Okay, so when we hear plasma, we usually picture the sun, right? That's what's called equilibrium plasma. Everything, the gas, the electrons, all of it is at the same ridiculously high temperature, thousands of degrees. But the really clever move here is to use something called non-equilibrium plasma. Now in this stuff, the gas itself can stay pretty cool, but the tiny electrons zipping around inside it, they're super hot, totally energized. And what you get is something that's chemically off the charts reactive, but without all that massive destructive heat. What this means is you can basically inject pure chemical reactivity right into a fuel mix, exactly when and where you want it. It's the difference between using a sledgehammer and a surgical scalpel. And that is the key to finally unlocking all the amazing potential of hydrogen fuel. Okay, so how does this cool plasma actually pull off this magic trick? Well, it works its magic in 3 different ways. You can think of them as plasma's 3 superpowers for combustion. So you've got these 3 main enhancement pathways. There's the kinetic, the thermal, and the transport enhancement. Each one plays a unique and critical role in making this all work. All right, let's start with the kinetic superpower, because this one is wow, just wow. Under normal conditions, some of the key reactions you need to burn hydrogen are super slow. They need crazy high temperatures, like over 1100 Kelvin, just to get started. But check this out. By zapping the fuel with plasma, scientists have shown that they can speed up a key reaction by about 1,000 times. And get this, at low temperatures. It's like creating a chemical superhighway that just bypasses the old, slow, high heat route completely. Okay, next up is the thermal superpower. And this is like a perfect double heat boost. First, you get this instant fast heating the moment the plasma is created. We're talking nanoseconds. But then it's followed by a slow heating over microseconds as all that energy stored in the excited molecules gets released. It's this 1-2 punch that gets the fuel mixture perfectly primed and ready for a super fast, super stable burn. And the speed here, it's just hard to comprehend. We're talking about nanoseconds. A pulse of electricity creates all these energetic, active species. Then, over the next few microseconds, they kick off brand new, way faster chemical reactions. So by the time you get to the millisecond timescale where normal combustion chemistry would just be getting started, the whole process has already been given this massive head start. It's already supercharged. So this all sounds amazing in theory, right? But the big question is, does it actually work in the real world? Let's get to the tests, because the results, they are seriously impressive. Okay, just look at this. In lab tests, if you just let a hydrogen-air mix ignite on its own, it takes about 860 microseconds. That's the auto-ignition time. Now add one quick pulse of plasma. That time drops all the way to 140 microseconds. That is almost 5 times faster. In the world of high-speed engines, that is literally the difference between an engine that works and one that just can't. And this isn't just a lab curiosity. These kinds of results have absolutely game-changing applications. We're talking about making scramjets possible for hypersonic flight, where you have to ignite fuel in an airstream moving faster than sound. It can also speed up the shift from a normal flame to a powerful detonation, which is key for next-gen engines. Plus, since you can ignite the fuel at much lower temperatures, you waste less heat, which makes just about any engine more efficient. And here's where it gets even cooler. The plasma actually creates its own little feedback loop that makes it even more powerful. It's wild. It starts like this. The plasma heats up a tiny bit of gas. That hot gas expands, so its density drops. But that lower density then actually boosts the local electric field. A stronger field creates, you guessed it, more plasma. And the cycle just keeps repeating, concentrating all that power exactly where you need it most. It's a self-enhancing effect. So when you put all this together, with this incredible potential, what does the future of fire even look like? What's next on the horizon? I think the researchers who did this work said it best. They described this whole subject as being ripe for further exploration. And that's exactly right. This isn't just about making the engines we have today a little bit better. This tech opens the door to creating completely new kinds of engines. Engines that could power a clean, hydrogen-fueled future. And that really leaves us with the big final question, doesn't it? The science? It's proven. It's incredibly promising. We've seen how plasma can tame hydrogen and basically perfect fire inside a lab. But now comes the next great challenge: engineering. Can we take this amazing science and scale it up? Can we engineer it to reliably and affordably power our cars, our planes, our entire world? The answer to that question, well, it might just define the future of energy as we know it.